the invitation for organizing this. I need to apologize to the rest of the audience in advance because I'm pretty sure there will be some overlap with your talk last week since you also spoke about the dark dimension, but I will try to make this self-consistent, so please excuse any kind of repetitive material. Okay, so the title of the talk is The Dark Dimension Warp Throat, which was a paper that came out last August with Ralph Blumenhagen, my supervisor, and Max Brinkman. And of course, the general framework where this project is taking place is the Swampland program, which is postulating that not all low-energy effective field theories can be UV related to quantum gravity. So the generic picture is exactly the one that I'm showing here. We have a bunch of nice-looking low-energy effective field theories. They have no problem a priori. They are consistent-looking, no anomalies, no other problem. But the idea is that as one is raising the energy scale, some of these theories become problematic and cannot couple to quantum gravity, and those belong to the so-called swampland with these alligators here, while the good ones belong in the landscape. And of course, one is telling this type of two theories apart by defining the so-called swampland conjectures. For reviews and references, I'm pointing to these three papers here because this slide didn't have enough space, let's say, to put proper references. And I would say that there are three main pillars of the Swampland program. The first one is the no global symmetries conjecture, which is postulating that there are no global symmetries in quantum gravity. This was already formulated before the official definition, let's say, the official start of the Swampland program. The second is the weak gravity conjecture, which per the name is saying that gravity should be the weakest force. And the third one, and the one that will be relevant today, is the so-called distance conjecture, which is always predicting some infinite hour of states at infinite distance limits. And I would discuss this more. And each of these conjecture, of course, has this related or derivative conjectures. And once again, I should put a disclaimer that this diagram here or this figure here is quite limited because there are many interrelations between these three pillars that I am not indicated here. And today I will focus on the distance conjecture and the ADS distance conjecture or generalized distance conjecture that was formulated in the same paper. So to the right-hand side of this figure. So the outline is the following. I will introduce these conjectures and how these, together with the smallness of the cosmological constant in our universe, lead to the notion and the proposal of the dark dimension. I will give a very brief review of work compactifications and how this leads to a warp throat realization of the specific scaling that is proposed in the dark dimension scenario. And finally, I will give a more concrete example regarding the large volume scenario. And also, I will point out some of the possible issues that arise in such type of realizations of the dark dimension scaling in warp throat manifold, let's say. Okay, so we start with the distance conjecture. And the setup here is a d-dimensional theory which is coupled to gravity with a moduli space M. This is indicated pictorially here. And the first part of the conjecture is that starting from some point P in the moduli space, one can always find some infinite distance limit in the moduli space. And this infinite distance limit is, of course, accompanied by specific behavior, which is an infinite hour of states with a characteristic mass scale M such that this tower of states is exponentially becoming light while approaching infinite distances. And such an infinite distance limit is the flat space limit in a 90 de Sitter background. And in particular, this led to the formulation of the anti-de Sitter distance conjecture, which claims that there exists an infinite tower of states with characteristic mass scale M, which, as we take the flat space limit, behaves as following. So we have the mass scale of the tower scaling like some positive power of the cosmological constant. And this power alpha here has a physical meaning. And in particular, in the case of ADS, it was postulated that it has to be larger than 1/2. And this guarantees that there is no scale separation between the anti-de Sitter radius and the internal manifold radius. And yes, And in particular, for supersymmetry vacua, there was also the strong version of this conjecture that claimed that alpha is precisely 1/2, but this will not be relevant today. What will be relevant today was some assumption or generalization that this same type of scaling should also hold for de Sitter, so positive cosmological constant. And this becomes relevant in the following sense, in this recent dark dimension paper by Montero, Vafa, and Valenzuela. And the idea is that when we are in the moduli space, depending on where in the moduli space we are, several quantities take specific values. And in our universe, we have very good indications that we are very close to some asymptotic limit. And these indications consist in the fact that we have some approximate global symmetry, which should not be there exactly, and also the value of the cosmological constant, which is very small. So the idea is that we are in this asymptotic regime of the moduli space, and then the Swampland program is postulating that the tower of light states should universally appear. And more concretely, we expect this ADC scaling, let's say, for de Sitter. So there is a tower which is scaling like some positive power of the cosmological constant. And once again, for de Sitter, this value of alpha has a physical meaning. There are bounds that depend on physics, and in particular, this upper bound, 1/2, is arising from the Higuchi bound, so it's guaranteeing unitarity. And the lower bound is actually coming from modular invariance in string theory and requiring that one is not overcounting modes. So the claim actually made in this paper was that this scaling in 4D, because this is relevant for phenomenology, should be precisely 1/4. And of course, if we fix this coefficient 1/4, we have a specific mass scale which is associated. And one should now try to look at the tower and see what the nature of this tower that emerges is. And here comes the emergence string conjecture, which is explaining what are the two types of towers that can arise in such an infinite distance limit. And in particular, we have either a decompactification or an emergence string limit. The main difference is that each of these types of limits is postulating a specific cutoff, upper cutoff in the theory. So a cutoff where, because of this tower of states arising, the theory can no longer be valid. For the decompactification limit, this is the higher dimensional Planck scale. For the emergent string scale, this is the emergent string case. This is the string scale. And in particular, we know that the cutoff in this case then should be this 2.3 millielectronvolt, which is very close to the neutrino scale. We know that we have an effective theory above the scale, so we can exclude the case of the emergent string. So we know we have some kind of decompactification case. And then there are experimental bounds that kick in, and there are surveys regarding supernova explosions or heating or cooling of neutron stars. And one can actually bound the size of the extra dimensions regarding in relation, let's say, to the number of big external dimensions. And in particular, there is only one case that is compatible between with experimental data, and this is the case of a single extra dimension. And this single extra dimension is what is called the dark dimension. So this is the main prediction, let's say, of this paper. So being at an asymptotic limit of the moduli space means that there is a tower of light states arising, which is signaling some decompactification to some large extra dimension of size of a few micrometers. And then the higher dimensional Planck scale, which is the so-called species scale, so the cutoff of the theory, where the effective field theory we started with is no longer effective, is given by 10 to this specific value here, which is 10 to the 9 to 10 to the 10 GeV. What is important here is that there is a need for a factor of 10 to the -1 to 10 to the -3 here to make this precisely compatible with experimental data. And what is also very important, and Eduardo probably told you enough about this already, is that the dark dimension provides has some very far-reaching phenomenological implication and provides very robust dark matter candidates, either in the form of Galucha-Klein gravitons in the extra dimension, or even primordial black holes. And it can be shown that these two approaches are actually compatible with each other. Okay, what is important, of course, in such a scenario is to have some kind of physical realization. And the idea is that matter should, standard model matter, let's say, should arise in localized regions of the eternal space so that the couplings are of the correct value, let's say, or at the correct parameter range. And in particular, what was proposed in the original paper was that there should be some kind of F-theory realization, and in particular, grand unified theory GAT7 brane, the volume of which is related to the higher dimensional mass. And knowing the size of the 7 brane, one can deduce what the size, knowing what the couplings is, one can deduce what the size of the 7 brane is. And it turns out that it is smaller than this large extra dimension, then it should be some kind of embedding, let's say. However, what is not clear is how can one actually reach some positive potential, construct quasi-de Sitter, let's say. And I would say this is where the main motivation for our work lies. And the idea is to try a different type of physical realization for this type of project. And instead of looking at some kind of F-theory realization, we are trying to reproduce this predictive 1/4 scaling in some Kaluza-Klein masses with regards to the cosmological constant. And the standard way to do this, let's say, is, of course, compactifications on a warped Calabi-Yau orbifold. So let me give a very brief review of the situation, the whole framework. The framework is, of course, a type 2B orientifold compactification on the Calabi-Yau threefold of volume V. And one is, as usual, stabilizing the complex structure moduli and the axiodilaton a la GKP by adding fluxes. Here, the three form flags has the following form. The axiodilaton is the following. The first part is the stray coupling as usual. And of course, one can then construct the superpotential a la of Vafa-Witten, and the fluxes induce some kind of warping that can be strong or not, depending on the regime we are studying. And then one needs at the later stage, let's say, are also stabilize the Keller moduli. And this can be done via non-perturbative effects. And this is some very common, two very common constructions, let's say, that provide a way to stabilize the Keller moduli are, of course, the KKLT model and the large volume scenario, which respectively use gains in a condensate and alpha prime corrections in the Keller potential. And of course, these two types of models are very popular or very well studied because they are providing some concrete way to reach the Sitter, the validity of which is disputed, but today I will not enter this discussion too much. And I will assume that most of the techniques, let's say, in KKLT and LVS work or assumptions. So the idea is that one is adding then some anti-83 branes that are localized at the tip of the throat. This is forcing their contribution to become exponentially small because there is a strong warping, and this can then give rise to a positive, small positive cosmological constant. Okay, so in particular, let's look at this throat. At the tip of the throat, we have the so-called conifold. This is given in C4 by the following curve, let's say. And topologically, this has a conical singularity, T11, which is an S2 times S3 of 0 size. One then needs to deform, let's say, or resolve the singularity, in particular, smooth out this. I would not say resolve, it's not a resolution, it's a deformation. And this is happening in the following way. So what is happening is that we now have a specific radius. We make the radius of this S3 sphere finite. And here I'm just putting this axis with S2, S3, just to indicate that these spheres exist. And in particular, I'm just explicitly showing the y direction, but you can imagine this S3 sphere being at each point here. So what is happening is that we smooth out the singularity with by making S3 finite. And then we have two types of cycles that are relevant. We have this A cycle, which is a 3 cycle that vanishes when Z goes to 0. So the radius of this S3 cycle goes to 0. And we have this B cycle that is dual to A cycle. And one is getting the famous Klebanov-Strassner solution by inducing or turning on specific three-form fluxes, in particular, M units of Ramon-Ramon flux through the A cycle and K units of NS-NS flux through the B cycle. And turns out that the total contribution to the touchable cancellation condition of these fluxes are also this, what I denote as N here, which is the product of M and K. All right. So let's go to a concrete warp throw description. And what we're actually interested in is the strong warping regime, where this combination of parameters, the volume of the Calabi-Yau and this conical modulus is smaller than 1, which means that we are effectively very close to the tip of the conical. So we have some Klebanov-Strassler throat of length YUV, which is attached then to the bulk Calabi-Yau. And this has been studied quite well in terms of stability of KKLT, the Sitter vacuum, and so on and so forth. Here I'm just pointing out some of the first references, and I will follow mostly the conventions or the results will be presented in terms of the paper of Ralph, Daniel, and Lawrence. So in order to study the following Klebanov-Strassler throat attached to Calabi-Yau, we start with N equals 1 supersymmetry action. This is determined in terms of the Keller potential and the super potential. Both of them have important Z contributions from the conical modulus. And then one is actually constructing the N equals 1 scalar potential. You can minimize, and one is finding that the conical modulus is stabilized at some exponentially small value, depending on the values of the fluxes. And here I'm not making any extra assumption. I'm not specifying any setup, not KKLT, not LVS. So we don't know if the solution is supersymmetric or not, and this is not important. We are keeping the setup as generic as possible. What is happening now with the relevant mass scales, and what are the relevant mass scales? Of course, we can directly compute the value of the conical modulus. It has this particular scaling shown here. It's clear that it's smaller than MS, so this is good in terms of the validity of the theory. We can also compute the masses of the other complex structure moduli, which are also smaller than MS. But actually turns out, because of GS m squared being large, that the conical modulus is the lowest complex structure modulus in our theory. And one, of course, should look at Kaluza-Klein modes. The easiest thing to look is the bulk of the Calabi-Yau, and one can estimate that we have some kind of isotropic Calabi-Yau. So this would be the mass scaling of the bulk Calabi-Yau, Kaluza-Klein modes, I'm sorry. And it turns out that if we express everything in terms of volume, they are as expected larger, heavier than the complex structure moduli. What is interesting is that there is an extra tower of Kaluza-Klein modes, which are localized close to the tip of the conifold. And their masses are given in the following sense. We have here again this combination of Z over V. We have some suppression by volume, so it's indicative that these are very light. But also the separation by GSM squared is important. And it turns out that these are around the same order as the conical modulus. The only difference is this extra parameter YUV, which is the length of the throat, and is conventionally large. Can be shown to be large, actually, at least numerically. And of course, the control of the effective theory is guaranteeing this hierarchy of masses. What are we doing now? The idea is that we're introducing this uplift potential in terms of anti-D3 branes that are localized at the tip of the throat. It has the following contribution to the potential. And of course, now we can use this uplift potential and this combination that appears here, and also in the mass of the light Calabi-Yau modes, to express everything in terms of the uplift potential. And now, one major assumption that one needs to make is that for a tiny cosmological constant, the value of the uplift potential should be very similar to the absolute value of the ADS potential. This can actually happen based on some appropriate choice of fluxes. And of course, now we can express, using this relation, the conical modulus in terms of the ADS potential. And the final assumption is that one can tune the final cosmological constant to be some kind of, let's say, product or expression in terms of the uplifted potential, but smaller than it. So we have this, parameterize all our choice to, or our freedom, let's say, to tune lambda to a small value in terms of this lambda prime. And plugging everything together, what's actually happening is that we have this precise 1/4 scaling. And these are the Kaluza-Klein modes that are localized in the tip of the throat. This is the cosmological constant, and this is directly of the same form as the predicted scaling in the dark dimension scenario. And what is important here that for this lambda, there is no prediction, physical prediction, let's say. There are some physical restrictions. And while here we can express this effective lambda parameter, let's say, in terms of the microscopic parameters of our model, in terms of the length of the throat and the fluxes. And one can actually turn the logic around and then say, since we know there are bounds for lambda, then we can also express this as a bound on lambda prime, which means that we don't have freedom to tune this final cosmological constant as much as we like, which is, in a sense, compatible also with the idea that the fluxes are quantized and we cannot tune also the z value as much as we like, and so on and so forth. And what is also relevant in this case is to check when the effective field theory stops being valid. And to this end, one needs to look at the species scale. The species scale is the upper bound of the validity of the effective field theory where the gravity is becoming strongly coupled. And in 4D, where one dimension is decompactified, the prediction, at least of the dark dimension setup, is the following. In particular, there is also another relevant proposal, which relates to the end of the validity of the effective field theory. And this is the emergent proposal. And this is claiming that kinetic terms, one-loop kinetic terms, come from integrating out massive states that are below this species scale. And one can actually relate the number of species, so the number of particles that are below the EFT validity, to this cutoff. And this was worked out in the paper of Ralph with Lawrence and Daniel. And they found that the species scale in the particular case of the throat was the following. It can be expressed in terms of this light KK modes, and it was actually lower than the predicted species scale of the dark dimension, let's say. So what this is showing us, what is indicating, is that one needs to be very careful. And the possible explanation is that one is not even looking at all the Kaluza-Klein towers that exist. We know that there are some other light towers that are in the throat. So in particular, there is this stray cycle that can also have some light towers that need to be taken into account in the combination, in the calculation of species scale, and so on and so forth. And in my last, I think, 2 minutes, I have this example of uplifted large volume scenario. So in this case, we have explicit expressions also for the Keller moduli. So we have one tau b, which is the big Keller modulus, which is the overall volume of the bulk Calabi-Yau given in terms of it, and also the small modulus, which is effectively the hole that one is poking in this Swiss cheese Calabi-Yau. And once again, the procedure is the same. Axiodilaton and complex structure moduli are stabilized by fluxes, and the Keller moduli are stabilized non-perturbatively at the specific value. And one can have a non-supersymmetric anti-de Sitter minimum, which is scaling like 1/value to the third. And the moduli bases are explicitly computed based on the scalar potential. And the one has the following hierarchy, let's say, of masses. So the Keller moduli are much slower. And now we have the expected hierarchy that we already saw in the generic setup. So we have the bulk KK modes at a high scale, as every bulk, pretty much every bulk field. And these small KK modes in the throat are scaling in a smaller power of V, so are much lower in energy. And of course, they are satisfying this predicted 1/4 scaling of the dark dimension. What's now interesting is that even though this looks like some realization of the dark dimension, there is one direct problem. And this problem is that if one compares the sizes of these Kaluza-Klein scales, and in particular also the lengths that arise, we see that the length of the bulk Calabi-Yau scale bulk Kaluza-Klein scale is only 3 times smaller than the length of the large extra dimension in the throat. And this in particular is in direct contradiction to experimental bounds, because this would mean that we have 2 large extra dimensions, and in the case of 2 large extra dimensions, the experimental bound is already 4 orders of magnitude smaller than this micron thing that we have already found as compatible explanation with a single extra dimension. So I think it's time to sum up. So the idea is that the whole dark dimension proposal is a very promising application of Swampland ideas that has testable experimental predictions or phenomenological implications. A string realization may be provided by this highly anisotropic compactification, where the single Tau dimension is arising naturally by looking at the direction that is along this highly warped throat. But it's very important to not just look at the scaling and say, okay, we found it, but we need to check compatibility with the other mass scales that appear in setup. In particular, the species scale should be the one that is compatible with the dark dimension scenario, and whether there are no other Kaluza-Klein modes that are spoiling this decompactification and making the setup having more than one, let's say, dark dimension, extra dimension. Okay, I think I finished on time, so thanks a lot.
Thank you. Thank you, Andriana, for the very nice talk. Let's all use our clap emojis. And we have some time for questions. There's some question. Irene, yes, you can unmute.
Yes. Hi, hello. Thanks for the talk, Andriana. Yeah, so I wanted to ask about the species bound. So the point is, typically, it's okay for our universe to have a tower which is so light for the lambda to the 1/4 if the species scale is much larger, because quantum gravitational effects can be very high. But here then I was trying to understand what is the conclusion, because you said that there is this possible species bound that is related to the Keke scale.
With the emergence in the throat, yes. So if one is...
But then that would imply that the species scale is of order lambda to the 1/4. So that would invalidate to have an EFT.
It would be, I would say, if this is actually the actual species scale, I would say it's a bit too low to say that this setup is already compatible with what we would expect, which would be the lambda to the 1/4 and 10 to the 9th JV, as in your paper.
Okay, so then that's important to understand whether like the KKLT deconstructions and so on have like an EFT, no? That you have a 4-dimensional effective.
Yes, or whether it's a 5-dimensional EFT, and then when you look at the species scale, you should not use the 4-dimensional species scale, and you should use maybe the 5-dimensional, and this changing the scale that is produced, and maybe this is compatible with the emergence, let's say.
And I was wondering also, maybe probably you know better, like, I don't know, the typical, are there models in which they try to fine tune somehow the modes of the throats that you try to decouple? I mean, how robust is the correlation between the lambda to the 1/4 and the Keke modes of the throat?
They have been confirmed numerically, at least in a paper by Ralph, Lawrence, and Daniel. So I would trust it as a result, but
okay, no, okay, it's a nice evidence that there are light towers in those setups, at least. Not at least. I mean, we have to explore more. But thank you for the talk.
Okay, great. If there's okay, we are a bit out of time, but it's a very short question. Maybe one can ask them. Otherwise, we should move on. Thank you, Andriana, for the very nice talk.
Let me stop sharing if I find where. Okay.
We're just on time. I may ask you something later, but.
Sure, of course. I'd be happy to discuss.